Okay, so now we are moving into op-amps and op-amp basics here, and I really enjoy this portion of the course. I mean, technically our first application was max power transfer. That's, as we've said, very important for being able to turn the crank, like running a DC motor, connecting up speakers in order to get maximum power out. But operational amplifiers, or op-amps, I should maybe write this out. Op-amp is short for operational amplifier, are an extremely important group of circuits out there. And first off, I'm going to draw the symbol for what an operational amplifier is. And we're going to start with just a basic one here. There are other ones that we might look at that have other connections here, but for now we're going to look at the fact that we've got really, it looks like it's a 5-terminal device, and it is 5-terminal device in a lot of sense, but 2 of these terminals are just power supply. So this is just positive power supply, and this is just a negative power supply. Now, what's really going on is this is representing a chip. And really what's going on inside the chip is a lot more. There's a lot more complicated circuitry going on inside the chip. And to illustrate the circuitry that's actually going on inside the op-amp, I'm actually going to pull up a window here, which is a datasheet for an LM741 op-amp. These are very basic, they're called general purpose. They're really used, I would almost say, in the classroom environment. Part of the reason is they're cheap, but they have some pretty good basic characteristics. But for other applications, we would need a more high performing op amp. Like for instance, this is not really good for using for audio purposes. It creates pretty noisy audio signals. But there are operational amplifiers that are designed for audio. So it's got the little supply here showing a typical application, which we're going to look at it eventually as far as what this application is. We've got all of this sitting here, but what I want to do is I'm going to scroll down on this data sheet some, and it's got like all the sorts of good information about the operational standards. I'm going to keep scrolling down, and I'm going to scroll down here to what's called the functional block diagram, and I'm going to zoom in here. Now, these are components here that we haven't talked about, and we'll actually be talking about in the next electronics course, but this is really what's sitting inside this chip. So we can see, yeah, there are some resistors here, but all of these other weird looking components here that are 3-terminal devices are called transistors. Some of you are probably familiar with that. We even have capacitor, but this is all sitting inside the chip. So that's all well and good, but what we want to do is I don't want to have to have this entire circuit diagram and keep analyzing this entire circuit diagram in order to analyze a circuit with an op-amp. So what we have here is the way this op-amp works here. We've got positive power supply and negative power supply. Is I'm going to draw it slightly bigger here, redraw it, and I'm going to kind of put in some circuit elements here to kind of show what's going on inside here. So we have our negative input and our positive input. And then we have a resistor here inside. So what we're doing is modeling. This is a model for that complicated circuit. And we label voltage here plus minus VD, which is referred to as a difference voltage. And then what we have here is we have a dependent power supply, and we have A times VD as far as what the voltage of that is, and this is connected to ground, this dependent power supply, and then we've got a resistor here, and then this is what's coming out of the output here, and this is just RO, and RO is simply just my output resistance. So we have some kind of voltage difference that's developed across this positive and negative terminal, and then we have A times that voltage difference, and then we have RO coming. So you can see where we're getting a voltage gain here is we're basically amplifying. A here is what we call the large signal voltage gain. Now, it turns out here, if we talk about what, and I'll put one other label here, this is RI, so this is my RI is my input resistance. And this is what we call is what's a non-ideal OpAmp. In other words, these are what would be considered even real-world op-amps. So real-world op-amps aren't going to be ideal because they're going to have some other parameters here. And if we go back to this data sheet here, let's go back and see if we can even find some of those. We can see here, large signal voltage gain. And it's given in the units of volt per millivolt. But if you have 200 volt per millivolt, really that's a typical value, and that's basically 200,000. So the large signal voltage gain is 200,000. And then it's got an input resistance here, and typical here we can see, 2 mega ohms. So it's actually got a pretty high input resistance. And then it's got like an output short circuit current. That's kind of important to know because that's essentially the short circuit current is, in some ways, that's telling you, well, how much current can you pull out of this device. And then there's also things like common mode rejection ratio, which when we get into some other courses we might talk about this. Having a high common mode rejection ratio is good for noise and also just for amplification. Supply voltage rejection ratio is also, having this as high means basically the supply voltages don't affect things. But then we even have transient response, and we have slew rates. Slew rates are important. Basically that's telling us how fast this op-amp is. And when we say how fast, well, if we have a high frequency signal, that means the voltage in a high frequency signal is changing rapidly. And so if it's high frequency and we don't have a high enough slew rate, the op-amp won't be sufficient. Now for most of the applications we're going to do, and in our lab, and then also in the lecture portion here, all of these things we're just going to assume are ideal, meaning that we have as high a slew rate as we need, it's as fast as we need it to be, we can put out as much current as we want, things of that nature. But clearly we can see those are not realistic when we're talking about real devices. But to have the basics of understanding these to start with, we start with just kind of making life easy and assuming ideal situations. So our ideal op-amp here. Let's talk about what our ideal op-amp is. Well, first off, for an ideal op-amp, the input resistance is infinite. Now, that's unrealistic. It's not. In fact, we just saw from the 741 that it was like, I think, what, 2 mega ohms? That's not infinite. That's clearly finite. But you have to think about what is it compared to the resistors if you're attaching. You know, if you're attaching a 2 kilo ohm resistor to the input here, so for instance, if I'm attaching a 2 kilo ohm resistor here, and it sees a 2 mega ohm resistor, Well, that 2 mega ohm resistor is 1,000 times bigger than this 2 kilo ohm. So in a sense, from circuit analysis standpoint, it kind of is infinite in comparison. I mean, it's so huge compared to this 2 kilo ohm resistor that you can almost say, well, it's kind of an open circuit at that point. Now, technically it's not, but that's where this kind of assumption is that, well, hey, these input resistances are very large. So for an ideal one, we will assume that they're infinite. But that consequence here gives me two very important things. I'm going to label two currents here, I negative and I positive. I negative equals I positive, which equals 0. Because if there's infinite resistance here for Ri, infinite resistance is the same thing as an open circuit, and we know no current. Because think about it, if you have a resistor with infinite resistance, well, voltage divided by resistance is current, so you're dividing by infinity, which doesn't even make sense to begin with. But if you're thinking, okay, well, infinity, that's just meaning it's a really huge number. Well, if you divide by a really huge number, you're going to get 0. So these two currents coming in are 0. The other thing that's going to be important for us here is that our large signal voltage gain is also infinity. We're going to assume that it's infinity. We have as much as we want. And with that being infinity, which again, we see that it's not infinity, but again, just on the 741, which isn't even an op-amp that, there's ones that have a much higher large signal voltage gain, but it was still in 200,000. Now, of course, everyone say, well, 200,000 is not even close to infinity because, of course, you could do, 2 giga or whatever. But the point is it's really large, and so we're like, okay, we're going to let it be infinity because it makes our circuit analysis a little bit simpler here when we're dealing with op-amps. And then the only other thing here is we're going to assume that the op-amp can supply any current we need. And even though that's not realistic, there's ways to get around that. A simple way that's just a mechanical solution is you could use the output of an op-amp to drive a relay. Have it be where the current coming out of the op-amp is enough current to charge a solenoid to flip a relay, and then you could have higher current going through that if you needed a higher current, like if you needed 1 amp or something. So I mean, that's a reasonable assumption to make as well. So these are the assumptions we're going to make, and then what we're going to do is we're going to, in the next video, we're going to analyze circuits with these assumptions. Our first goal is going to be, amplifying. So we're going to have some input voltage and we want to amplify it. We want to make it bigger.